All right, so we're going to be looking at the area of circles and circle sectors, and the argument that we're going to make here in terms of being able to show where this equation comes from, the area of a circle being pi r squared, is we're going to take a circle here. We're going to use that process that we looked at earlier of dissection, in which case we're going to cut this circle into 4 pieces, specifically at 90-degree angles, and then we're going to take these pieces and rearrange it so that they form this figure. Now, you might say, well, why are we doing that? Well, it kind of leads to this idea. Notice it's starting to look a little bit, not quite, but almost more like a parallelogram. Okay? So what we're going to do here is we're going to cut the pieces even smaller and smaller and see if we can get more into a parallelogram type form. Okay? So if we cut instead the circle into different pieces here at a 45-degree angle, okay? So now we have smaller pieces. Then we take those pieces and rearrange it. Notice it's starting to look more like a parallelogram, okay? It's starting to look more like a parallelogram. Then if we cut them even smaller, so it's 30 degrees, and then we rearrange it, it's even closer to a parallelogram. And then if we cut it even smaller yet at 15 degrees, well, now it's definitely starting to look like a parallelogram, okay? Now, the idea here is that if we continue to cut it smaller and smaller and smaller, in a sense, infinitely smaller, that eventually we would reach an actual parallelogram, okay? So if we could cut the pieces infinitely small, we would end up with a parallelogram. Well, what do we know about the area of a parallelogram? Well, the area of a parallelogram is the base times the height, okay? Our area is the base times the height, okay? So keeping that in mind, if we take one of those images that we saw before, our base here, notice when we take those pieces and we rearrange it, half of our circle, the outside, ends up here, and the other half ends up here. So in a sense, half of the circumference makes up this piece, and the other half of the circumference makes up this piece. Well, if that's the case, go back to what we know about circumference. Circumference is 2 pi r. Well, if this piece only takes up half of that, if I divide this by 2, we're left with pi r. So our base here, the base of our parallelogram, is pi r in length. Pi times the radius. And the height here, notice if we look at our pieces here, okay, each one of these pieces comes from this guy, okay, where this piece from the center to the outer edge is just a radius, okay, it's just a radius, okay. So if we look at this piece here, eventually, as things get straighter and straighter, notice from the center piece to the outer edge, this length here is nothing more than a radius. So the height here, like they're showing here from the center of the circle out to the outer edge of the circle, is just the radius, okay? It's just the radius. And as we continue to go infinitely smaller and smaller and smaller, the height turns into the actual length of the radius, okay? So with that in mind, that guy represents the height. Well, looking at the area of a parallelogram, base times height, our area, the base being pi times r, times the height, which is r, the radius, we end up with the area is pi r squared, because r times r is r squared. Okay, so that's where that guy comes from, the area of a circle. Now, what's useful about that is then if we're given a circle, and we know what the radius is, like in this case, we know the radius here is 9, then we can take our equation, which I know it's written to the side here, but I'm just rewriting it, pi r squared, and we can plug in 9, that's our radius here, 9 for our r, and then just solve. So we get area equals pi times 9 squared. Well, 9 squared is just 9 times 9, so we get 81. So in other words, the area is 81 times pi, because it doesn't matter which order in which we multiply things. So we get 81 pi yards squared, okay? Now, if we're looking for the exact answer, again, on your calculator, you could take 81 times our pi, okay? You have to use that second button. And then when we multiply that out, we get what they have there, approximately are 254.47 yards squared. Okay? Now, if they don't give you the radius and they give you the diameter, it's still the same process. Just remember, radius is half the diameter. So in order to use the radius here, if the diameter is 10, then half of this would be the radius, correct? Well, what's half of 10? 5. So the radius here is 5, and then we go through the same process, okay? Area of a circle is pi r squared, okay? In this case, our r is going to be 5. 5 squared means 5 times 5, so what's 5 times 5? 25, and we get 25 pi. So that would be the exact answer, and then again, if we actually multiply it out, we get approximately 78.54 centimeters squared. Okay, so 25 times pi gives us 78.54 centimeters squared. Okay, now that's the area for a whole circle. If we just want to find the area of a sector of the circle, okay, this plays very similar to the idea that we looked at with arc length. Okay, so remember when we looked at arc length, we only looked at a portion of the circle. In other words, we only looked at from the central angle a certain number of degrees in which we were looking at for the circle, okay? And what we did is we took that central angle divided by 360 to represent that part of the circle that we were talking about, okay? For instance, a semicircle, we took 180 divided by 360 because we were only looking at half of the circle. Well, when we're finding the area of a sector of the circle, okay, a circle sector, it's the same idea. If we're looking at half of a circle, that's 180 degrees of the circle, we could take 180 out of 360 and then multiply that by the area of the whole circle, okay? So we're only talking about half of the total area, okay? 180 divided by 360 is half. If we're looking at 90 degrees of a sector of a circle here, we could take 90 out of 360, which is just 1/4 times the area of the circle, and that gives us 1/4 of that area, 1/4 of the area of the total circle, okay? And so that still applies when we're looking at other angles as well, such as 49 degrees out of 360 times pi r squared. And then eventually, and I think what we used was actually theta, but we could use x here, in which case we're talking about the angle, the central angle divided by 360 times pi r squared is going to give us the area of that sector of the circle. Okay, so that's what this guy is here, and I actually prefer using theta versus x, so that's what I'm going to put there. Okay, so with that in mind, let's look at finding the area of this guy here. So area is going to be theta, that central angle, that portion of the circle we're talking about, divided by 360 times pi r squared. So the area, our central angle in this case here, is 195 divided by 360 times pi r squared. Whoops, let's go back here. We know what r is. R is 6. Okay, so let's actually plug that in. So we get 6 squared. Okay, well, this is where we can use a calculator to kind of help us out. Now we know 6 squared is 36, but we can actually multiply this out all at once. We could take 195 divided by 360 in our calculators. Then if you hit times and hit either the second or shift key for pi and find your pi symbol, times 36, then we should get, if we're looking at an exact answer, we'd have 39 over 2 pi, which comes out to be approximately 61.26 feet squared. Okay, then if we wanted to write it as an exact answer, we could say 19.5 pi feet squared if we didn't multiply by the pi, but if you're multiplying it all the way through, we get 61.26 feet squared. Okay, let's try one more of these. Okay, so again, we're taking the area is our theta, that central angle, divided by 360 times pi r squared. In this case, our central angle is 30, so we have 30 over 360 times pi, and our radius is 12. Well, multiplying that out, let's actually find the exact value first, and then we'll multiply by pi. Take 30 divided by 360, and then multiply that by, well, what's 12 times 12? 144. So we could just multiply it by 12 times 12 or multiply it by 144. That's our 12 squared. And so we end up with 12 pi, 12 times pi. So again, that's the exact answer, and then we actually multiply that by pi. If we take 12 times pi, then we get about 37.70 centimeter, whoops, jumped all the way off the page there, centimeters squared, okay? So that would be our answer there, okay? Now, we could get to other examples as well in which circles are involved and when we want to find the area of a composite figure. So if that's the case, like if we look at this example here, notice I have a semicircle attached to what appears to be a trapezoid, okay? We have two parallel sides, and we have one pair of parallel sides, that's what I meant to say. And then we have our height given to us, one of the bases, and then of course, since this is 5, notice we have 2 tick marks, this is also 5, which means if this is the radius, so if we're looking at this guy, if this is the radius of this semicircle, doesn't that mean this length here is also 5? Yeah, okay. So if that's the case, this would also be 5 because it's the radius of that semicircle, okay? So actually what we end up here is we have a semicircle and we have a trapezoid. So we're going to add the two areas together to give us the total area, okay? So let's work through this example here, okay? Let's find the area of the semicircle. Maybe we could say AS, okay? In which case, the area of the semicircle here is kind of like the sector problem we're working with. We have theta, the central angle, divided by 360 times pi r squared, okay? So we have the area of our semicircle is going to be, in this case, if we have a semicircle, what is this angle here? 180 degrees, right? 180 degrees forms a straight line. So we have 180 out of 360 times pi r squared. Well, what's our r? 5, okay? So our radius over here, our radius over here is 5, okay? So then we're just multiplying this out. 180 divided by 360, we get 0.5 or a half. And then if we take 5 squared is 5 times 5, that's 25. So we have 25 times 0.5, and we get 12.5 pi. Okay, so the area of my semicircle is 12.5 pi. Now I'm going to leave it like that for now because we have to add in the area of our trapezoid, okay, because we want the total area. So we're going to add, this is our area of the semicircle, okay, and let's call this maybe AT for the trapezoid, and we're going to add in the area of the trapezoid. Well, how do we find the area of a trapezoid? Remember, the area of a trapezoid is 1/2 the, 1/2 base 1 plus base 2 times the height, okay? Well, in our case, we know that our base 1 is 5, and our base 2, notice, is made up of our our radii here, 5 and 5, makes 10, okay? So this total length, maybe try a different color, this total length is 10. So I know base 1 is 5, base 2 is 10. What's the height? Well, our height is given to us over here, which is 3. Okay, so we have enough information here. Let's just go ahead and find the area. The area of our trapezoid is 1/2. Our base 1 is 5 plus 10 times our height of 3. Okay, so then we have the area of the trapezoid is 1/2 times 15 times 3. And we can multiply this out. We have 15 times 3, and then we divide that by 2. We get area of our trapezoid is 22.5, and of course it'd be centimeters squared. So we should actually probably write that over here too, centimeters squared. Okay, so we have the area of the semicircle and the area of the trapezoid, and what we want to do is we're going to add those two together. So we have our AS plus the AT, which is equal to 12.5 pi plus 22.5 centimeters squared, okay? Now, if we want the exact answer, in other words, this represents our total area here, it would be 12.5, in our calculators, 12.5 times pi, okay? Find that guy, and then add 22.5, and so what we end up with is about 61. We end up with about 61.77, it looks like, 77 centimeters square. Okay? And then we can go over these other examples in class. Of course, this again, we can find the area of the semicircle. Notice there's 3 of them, so we can add up 3 of the same measures. Then find the area of the square, add that together for the total area. And then in this example here, they're wanting to find the shaded region. So what you would have to do is find the area of the trapezoid and then subtract the area of the circle, because they only want this region here. So this one would end up being subtraction. Okay, so it's kind of the opposite of what we just did. Find the area of the trapezoid and subtract the area of the circle. Okay, so we can cover this in class, but of course they also have the information written here if you want to look through that as well.